Hi everyone. So in this video, I'm going to be going over how to model circular motion with Ferris wheels, and then I also have an example about a wind turbine just to switch it up. This is your week 14 optional practice, and I'm going to go over the exact problem. So either maybe you tried it already and you're just watching this to check your work, or maybe you're just going to do it along with me. Either way is fine, whatever works best for you. So for the first one, we're going to use the information to answer the questions about the Ferris wheel. So we're going to start by labeling the Ferris wheel with the information we've been given, because that's just going to help us to visually understand what's going on. So the first piece of information we get is that the center of the wheel is 32 feet off the ground. So I'm going to mark the center of the wheel to the ground as 32 feet. So that's going to help me remember. And then the radius is 24 feet. So I'm just going to mark one of the spokes as 24 feet because we know the radius is from the center to the edge of the wheel. So I will make this a little more clear. Okay. Then we know the wheel is moving in the counterclockwise direction. So that means starting at point A, it's going around to the left and down and then up. And we're always starting at point A, which it will remind us as we ask the questions that we're starting at point A. So it says, how high is the rider at the highest point and lowest point on the wheel? So the highest point, even though it's not marked with the spoke, we know the highest point is up here, highest point, and then down here at the very bottom will be the lowest point. And we have done a few examples like this in class, so by now we know that to get the highest point on the wheel, we need to add the height of the center plus the radius, because the height of the center gets us from the ground to the center, and then adding the radius gets us to the top of the wheel, so then we finally will have the height of the top of the wheel from the ground. So for the highest point, we're going to add 32 plus 24, and that gives us 32 plus 24 gives us 56 feet for the highest point. So I'm going to mark it there just so I have it. And then the lowest point, we know that to get the lowest point, we're trying to find this missing piece right here, and we already know the ground to the center is 32, and then this part right here is just our radius. So to get the lowest point to the ground, we can just subtract the height of the center minus the radius, and it'll give us that leftover piece, which is the height of the lowest point from the ground. So I'm going to do 32 this time minus 24, and that gives us 32 minus 24 gives us 8 feet. No, that's wrong. No, it doesn't. No, that's right. It is 8 feet. 32 minus 24. Great. I'll mark that right here. So you can always remember that to find the highest point, you're adding the height of the center plus the radius, and then to get the lowest point, it's always the height of the center minus the radius. So you can remember it's kind of always that same pattern, just depending on what numbers you have. Now it says, how high off the ground is the rider at point C? So for point C, that's going to be a little different because it's not exactly at the highest or the lowest point, it's in between. And this is where the right triangle comes into play. Okay, so you might think about a right triangle here, and you might think about, we would need to know the degrees, and we would need to find this height. We know the radius is 24. And this height plus the height of the center will give us the total height of point C. I just realized I skipped a question. Sorry, I'll go back up. How many degrees has the rider rotated from the starting point A when they are at point B? Well, this is pretty much also part of what we need to know for question 3. We need to know how many degrees are in each section. So we want to count how many sections do we have. We know there's 360 degrees total in a circle divided by the number of sections. There's 6 sections. So that gives us 60 degrees total in each section. And from point A to point B is only one section. So 60 degrees is going to be the answer. From point A to point B, it's going from 0 to 60 degrees. So 60 degrees is how far they've rotated from point A to point B. If it was farther than point B, we'd have to keep adding 60, but it's only one section. So now how high off the ground is the rider at point C? So again, if you might want to think and remember how we would use a triangle, we know now this is 60 degrees, and we would be looking for the height. We know the hypotenuse, so we always use the sine function. But we also learned that we don't really need to set it up like this every time. We don't need to draw the triangle and do all this work because it's always the same pattern. We're always going to be doing the radius times the sine of the angle plus the height of the center. And I can remind you the reason why is if we did set up our sine function for this triangle I drew, so we're trying to find the height, which is the opposite side from 60 degrees. So sine of 60 degrees equals the opposite side over the hypotenuse. And then we would multiply by 24 on both sides. And then we would put 24 sine of 60 in the calculator, and then we would add on the 32. So it's always the same pattern. We have the radius times the sine of the angle plus the height of the center. So we're going to just use that expression to find the height of the rider at point C. Now, we usually want to use the angle of rotation, which is basically saying, you know, how far have they rotated at point C? They've rotated 60 to get to point B, and then 120 to get to point C. Now, you might be wondering, why are we using 120 when over here we had 60? I can show you in the calculator that sine, and we're going to learn a lot more about why this is later on. Oh, I think I need to type the angle first. Sine of 60. Oh, I think I did that wrong. Isn't it? Oh, no, it's in radian mode. I need to switch it. How do I switch the mode on this calculator? Oh, the degree. Okay, 60. So sine of 60 gives us 0.86, and then sine of 120 also gives us 0.86. And again, we're going to talk about why that is later, but actually, when we use the angle of rotation, it gives us the same sine value as if we used that 60-degree angle we drew in the triangle. So we're going to use the angle of rotation because that's what we want to be able to do in step 4. We want to be able to find the equation based on the angle of rotation. So I showed you all this just to recap why we're doing it this way, but you can just always remember that to find the height off the ground of the rider at any point, it's always the radius, which is 24, times sine of the angle of rotation, so 120 degrees, plus the height of the center, which is 32. So I'd be putting 24 sine of 120 plus 32 in the calculator. I'm going to pull up the Desmos calculator. 24, make sure it's in degree mode, sine of 120 plus 32 gives me 52.78. So 52.78. And that makes sense. I mean, think about it. The highest point is 56 feet. C is a little lower. So always make sure your height makes sense, because it makes sense that C would be a little lower than the highest point we had already found was 56. So now to write an equation that models for any angle of rotation theta, we're literally going to write an equation that is the same format, but instead of putting a specific angle in, we're going to put theta in because we want this equation to work for any angle. So H of theta, so the height based on the angle of rotation, is the radius, 24, times sine of whatever angle, any angle of rotation, it would work for anything. So we put in theta as the variable to represent any angle, plus the height of the center, which is 32, okay? So it's always the height of the center being added at the end, whoop, and always multiplying by the radius, and we're always using sine, okay, of whatever angle, okay? So on the next one, I'm going to try and show you again how we don't have to draw the triangle. I won't draw a triangle this time to prove to you that we don't have to do that step. We can just remember this pattern for every circular motion object we look at. So this time we're looking at a wind turbine. The center of the wind turbine is 292 feet off the ground. I kind of already have a marking here to mark this. So 292 feet. And then the blades are all 190 feet long, 190 feet. So that's our radius. I'm going to write that down, that it's the radius, since it doesn't specifically say that, but if that, the blades are definitely our radius here. And then the wheel's moving in the counterclockwise direction, so same as always, going in this direction. And it's a little different because we don't have a rider this time, but we are still starting at point A. So how many degrees has the blade rotated from the starting point A when it is at point H? So that's a pretty big rotation. We're talking all the way around to here. So it would help us to first know how many degrees are in each section. So 360 degrees divided by, there are 8 sections, and we know that's 45 degrees in each section. So to get to point H, I would just need to add 45 until we get to H. Another technique you could use is that since we know the whole circle is 360, and this rotation is all but one of the sections, we could just do 360 minus 45, and that would actually give us our answer, 315. So you could add 45 7 times, or since we know the whole rotation is 360 and we're just trying to exclude the one last section, it's 315 degrees total. And then how high off the ground is the tip of the blade at point F? So point F. Now this time we're looking at one of the points that are below the center, and we're trying to find this height. So we're trying to find the height of F from the ground. And we know that we're gonna have to do, if we were making a triangle, we'd be doing some subtraction, but we learned in class that when we just use this pattern and we use sine of the angle of rotation, it's going to automatically give us a negative number. So it's going to take care of the subtraction for us. So I really don't even need to think super hard about this. I know it's always the radius times sine of the angle of rotation plus the height of the center. So my radius is 190 times sine of the angle at point F. So I just need to figure out my angle of rotation at point F. That's 45 plus 45, it might help just to label. So 45, 90, 135, 270, and, oh, not 270, sorry, 180, and then 225. So F is 225, so I do 190 times sine of 225 degrees plus the height of the center, which is 292. All I need to do is put this in my calculator, 190 sine 225 plus 292. We'll see if I can remember. Sine 225 plus 292. Aha. 157.65 feet. 157.65 feet. I remembered that number right. And if I mark that here, we could find the height at the highest point and the lowest point and make sure it makes sense. We definitely know it's supposed to be less than the height of the center though, so I think that helps just to know the height of the center is 292. F is definitely going to be lower than that, so I think this seems like a height that makes sense. And then our equation is just, okay, H parentheses theta, the height based on the angle of rotation, equals 190, that's our radius, always our radius, times sine of theta, because we want this to work for any angle of rotation, plus the height of the center, 292. So I didn't even draw a triangle for this one because like I know it's going to work. I know that this setup is always going to work no matter what circular motion I'm looking at. So hopefully this helps you to prepare for your quiz, and let me know if you have any questions.